as Adam described, I'm a postdoc researcher at Microsoft Research, and most of my research is in understanding the relationship between prediction and causation. So what I'm going to do in this talk is to just give a very, very broad overview of why we should care about causal inference. And I'll give you examples on why we should. And then I'll also try to show you that it's not just that it's good in a very academic sense, because you feel happier if you know the causes. It's also helpful to evaluate the systems that we build, like recommendation systems. And it's actually also useful to make predictions more robust. And I think the goal for this talk would be to sort of mainly focus on why we should care, because I'll show you a lot of examples where you can get really, really bad results if you're not careful about that. And I'm hoping that with that motivation, there are lots of other tools that I'll point to which can help in points second and third. So I'll just sort of briefly go over the point second and third, but really the goal of this talk is to understand why should we care, especially when we have increasing amounts of data. We have data about all the properties, all the users, about any online system if you have access to the logs. And we can do really good predictions. I mean, this conference, I guess, it doesn't need to be said that there are lots of machine learning advances that are helping us make great predictions. So here's some examples. We can recommend people what to buy, what to wear, who to date. We can find fake activities. We can find fraudulent activities in money markets. And we can also give really, really good search results, right? So in terms of prediction, if you give me a problem and say that this is what I want to predict, we are very successful. And so let's just look at a few seconds on how does prediction work, very, very bare bones view. Suppose you have a problem of finding out which users will contribute more to your platform in the future, right? So these are Xbox users. So maybe at Microsoft, we want to know which users will play more games in the future and which would not, right? And so one answer would be that let's just make it a prediction problem. So we'll collect a lot of features about the users, maybe their age, gender, past activity, social network, and so on. And then we can simply say that their final activity is just a prediction function of their earlier activities, right? And this is what we find in practice. So if you look at this user, they have a lot of friends. And if you look at the other user who have lower activity, they have no friends, right? So if I make a prediction algorithm that just takes the number of friends and the logins in the past month, I can predict with really good accuracy who's going to come back in the next month, right? And this is almost like a solved problem. You can get packages to do it. But the question then becomes, once we've made this prediction, so what? If I was doing this and I would take this to my boss, they would ask me this question. So that's good. OK. So we know that people have more friends than they play more. What do I do with it? How do I now make more people play more games on Xbox? Because that's what my boss wants to do. So here's the then causal question then comes up, right? Would increasing the number of friends increase activity on Xbox, right? It clearly predicts well, very high accuracy. But do we know that? Well, let's think about it, right? So if it's the case that having more friends makes you much more likely to play more because you feel a part of the community, yes, right? And this is what this model is showing. Each node is essentially a variable. So here, number of friends. And each arrow shows the direction of causal connection. So this graph essentially is saying number of friends causes Xbox activity. Great. But what if it's the opposite? What if all that's happening is that just the people who play a lot of games also make a lot of friends just because they're playing games, and while playing games, they meet new people? If that's the case, then our model may not really help that much. And what's insidious is that maybe both of them are not true. Really, something else is happening. Like, what's maybe happening is that there are just these some people who like playing games, and if you give an Xbox to them, they'll both play a lot of games and make a lot of friends. But if there are the other kinds of people who have an Xbox, they would do neither of those things. And any effort to increase their friends or any effort to increase their activity would not affect any of the outcomes. And so really, the key question becomes that once we have these models, how do we know what causes what, right? And this doesn't happen in just Xbox systems or prediction systems. In the next couple of examples, I'm going to show that this is sort of a problem endemic to the whole online system and online platforms world. So let's take search engines, right? If you read any marketing journal or article, they'll say that search ads are the best. They get about the highest CTR compared to display ads and any other ads that you can think of, right? So this seems like great. Oh, search ads really work well. But again, do they really? So if you want to predict when a user searches for Amazon toys, what is the most relevant ad to show to them? We are very, very accurate, right? You can try this for most queries. I'm sure a lot of you have noticed this. The ads would be really relevant. And once I see an ad for Amazon toy at Amazon.com, that's exactly what I wanted. And I would click on it, right? And so in some sense, you might think that, wow, you're getting high click-throughs. But the question again begs, what's the counterfactual, right? What would have happened if Amazon did not pay Bing for those ads, and instead the user was just forced to look at the organic search results? Well, the answer is they would have also seen the same links in the organic search results. And so it's a sort of an empirical question, to what extent are these ads actually helping Amazon gain new customers, right? And if you want to think of the graphical model again, and this is very nice because thinking of in terms of graphical models helps us expose these sort of complicated procedures into very, very simple principles. So it could be that search ad causes visits to toy website. Great. Then you should spend a lot of time and money on Bing ads. Good for Microsoft, too. But it could be just happening that it's just a search query, right? There are some people who are interested in toys. They issue search queries. They are more likely to click on the search ad. They're also more likely to go to the toy website anyways. And then there are just lots of other people who are not interested in toys. Maybe that's the ones you want to show ads to. But if you use this approach, you're not going to get them. But you'll still get a high CTR, right? So the whole point of this example is that when we look at observational metrics, and when we look at how great our models are at predicting what a user will do, they are good at exactly that. But they are not good at the counterfactual. What would a user have done if we had not spent money on this item, or if we not had this new feature that we built? And so you might think that there are some concocted cases like these in search, in recommendations, but actually they apply almost anywhere. So even if you look at offline ads, like display billboards, right? Let's suppose Toys R Us has a display billboard ad in streets, in newspapers, everywhere, because it's December, right? They think that we have a lot of inventory that we want to sell, and so we're going to make really, really creative ads and put them across on all areas. Clearly, they might find that their ads did really well, and sales shot up compared to the last month. So one answer is the creative was really good, so we should reward our designers. Another answer could be that people got a lot of interest in toys because of these ads, so ads are really effective. But then if you think just a little bit more, it doesn't take a lot, you'll probably realize that December is when most of us buy toys, because it's holiday season, and we want to go and give toys to kids. So what might just be happening is that irrespective of the intent, irrespective of the ad, irrespective of the creative, it's just that if you show ads in December, or if you do anything in December, your clicks and your purchases are going to go up, right? So what you might be doing well off is actually comparing it to December of the last year, or maybe doing something more comparative than just comparing it to last month or a week before. And so really, if you think about these cases, you might be still wondering that it's just, we just overestimate, right? There is an effect. I believe there's an effect. We just overestimate. Maybe it's OK, right? But let me show you something else. It's not just that we overestimate or we underestimate. If we're not careful, we can gain completely wrong conclusions. And this is a point that surprised me as well. This was a study we did on Reddit, which I'll show you. which was just, it took us weeks to understand what was happening, but once we got it, it was clear that it was another problem of causal inference, and we just got entangled into reading too much in the observed data. So how does this happen? Let's suppose you want to evaluate a new recommendation system, or really any new algorithm, right? And the only thing you have is past observational data. So you can't do an experiment, right? So you think, OK, maybe there are other ways to figure it out. And so what you might do is you have algorithm A, you have algorithm B. Very carefully, you can sample past impressions of both algorithms, right? So you have the first algorithm, which predicts recommendations. And then you have the second algorithm, predict recommendations. And you can look at the CTR. So you might find that the old algorithm on 1,000 impressions does 5% CTR. Very nice. The new algorithm does 5.4. And so that's a very nice result, which is telling you that algorithm B is better. And so you go to the decision makers and tell them that, yes, you should continue with algorithm B, because in the observed logs of the system, this clearly has a bigger effect. But then they might ask you, that's great, but we also want to know how this algorithm is affecting different kinds of people. So for example, they might know in their domain that higher activity people actually contribute a lot to their platform than lower activity people. So they just want to know how this new algorithm is affecting different segments of people. So you say, well, great. You go back to your data set. You segment the users into higher activity and lower activity. And you look at the CTR. And here's what you find. For lower activity users, the CTR for the old algorithm is better. And for higher activity users, the CTR is again better for the old algorithm. Now, at this point, you might be wondering that I'm just making some error in computing what's going on. But really, this is all I'm doing. I just had 1,000 impressions. I looked at the total CTR, which is right at the bottom. It's out of 1,000, 50 clicks. Out of 1,000, 54 clicks for algorithm B. This is better, right? And just when I condition on higher activity and lower activity, I find exactly the opposite result. So for old algorithm, I find in both cases, the CTR is better. Any guesses on what's going on, or what might be the problem here? And so one hint you might get is that these numbers look really different, right? So somehow, for the new algorithm, the higher activity users got almost 80% of the views. And somehow, for the lower activity users, it was the reverse, right? So double the number of users were seeing the old algorithm versus the new algorithm, right? So this should give you some hints that what was happening was that just this sort of selection effect, where the people who are likely to click more, the higher activity users, somehow always went into the condition for the new algorithm. And the people who were clicking less somehow always went to the old algorithm, right? And just because of this sort of underlying variance in your data, you were getting completely nonsensical results. And the sort of unsatisfying part is that even after discovering this, you might be tempted to think that actually the old algorithm is now better. But I don't think even that's true. Because what might be happening is that we controlled for the activity level, right? So again, if you look at this diagram, we were supposing to get this effect, so recommendation algorithm to CTR. We got a positive effect for the new algorithm. But then we controlled for the activity level, because we thought that would matter. So we got a better result, which was that the old algorithm was better. But who knows what other things were happening in the data, right? So here's just one example. Maybe there was a time of day effect as well. Maybe for some reason, or whatever bug or whatever engineering building, you might have found that the time of day was also factoring in. So the new algorithm was shown more in evenings. The old algorithm was shown more in mornings, right? And it's entirely possible that if you condition on that too, your result will flip again. Or maybe it will just become insignificant. So really, my point of this is to show that there are valid methods when we can condition on things we think would matter. But really, after a point, it's just a matter of knowing what your system is. With these kinds of methods, the best we can do is approximate to the truth. Here's another example. This is a personal example that I found while working on Reddit. And it took us weeks, as I said. So I was working with a PhD student, and they took the entire Reddit data set from 2008 to 2014, right? So there's no sampling bias. There is no API restrictions. We have the entire Reddit comment history of everyone who commented at any point of time. What you find is that if you look at the years, and on the x-axis I have the years from 2008 to 2014, the comment length is decreasing over time. And that's the sort of purple line that's going down, right? So what's happening is if you were Reddit and you were looking at the average comment length in 2008, it was high, around 220. And if you were looking at it at 2010, 2011, it's about 180 characters per user per comment. And if you're looking at 2014, it's gone down to 170. Clear cause for concern if you're Reddit, because what's happening is that for some reason, people are just starting to comment less and less. And so we thought of theories like maybe what's happening is that when Reddit was smaller, people felt a more sense of community, so they were commenting more, and now it's just become a big mess, so people probably don't associate that much with Reddit, and hence don't comment that much. Yeah.
Your sample size is one representative.
So that's the interesting point. We have the entire Reddit comments. We did not take a sample. So there was an API which could allow us to access Reddit comments, and we sort of swept through entire history. So this average is across all the comments made ever from 2008 to 2014.
Like once in 2000, you might have like 1 million comments in 2014. And
right.
10,000 in, you might have like 1 million comments in, or 100 million comments in 2014 compared to like 100,000 in 2008. So it's not really an accurate distribution. Right?
I see. So that's an interesting question. So yeah, the question essentially is that maybe what's happening is that there were lesser comments earlier on, and then the comments become more and more as you go on. So I think that would matter if the sample was smaller. But because we had, even in about 2008 and 2009, we already had more than 1 million users on Reddit. So the error bars on these are really small. So you can essentially plot this mean with the error bars, and they are almost indistinguishable. So that could have been happening, but at least at Reddit scale, it's very unlikely that was the case. But then we found something else. And by the way, if you have any questions, feel free to just jump in. Yeah?
What if they had introduced a mobile app? They just switched to a mobile app, which naturally reduces the amount of comments they do.
Yes, and that's a good suggestion, yeah. So maybe that was happening. And this is the sort of thing that is so interesting about these problems, is that we can come up with a lot of theories, but it's just hard to know what was actually going on, right? But let me show you another plot which might help us gain some understanding. So what we did then was, instead of looking at the overall comment history, we just picked each user whenever they joined Reddit and just plotted how their average comment length is increasing over time, right? So what I'm showing you now here is time in user referential, which essentially means if you joined in 2008, you start from here. If you join in 2014, the graph still starts from here. It just starts at a different level, right? And what we find is that for every user, for every year that they joined, their comment length is increasing, right? The only difference is that people who joined earlier in 2008 would start at a much higher level. They would already be commenting much more, and they would sort of then increase their level of commenting as they grew on. The newer users, for whatever reasons, they're millennials or they're using a mobile app, they were just starting from less comments per post, increasing still, but just starting from less comment posts. And that's all that was happening, right? So it wasn't that Reddit had to discover a new way of making people want to comment more. People anyways were, once they started from whatever level they had, they were always going towards a a tone of commenting more and more and more. So the problem wasn't they wanted to comment more. The problem was just the selection effect. The new users who were coming in were somehow just not in a style of commenting more, right? And so once you discover this, your solution may be very different from what you might be if you thought the comment length was a problem, right? In simple terms, what people in the social sciences say is happening is selection bias. In other words, the population of people that come in each year is changing. And there's only so much you can do except know exactly what kinds of people you're targeting and what kinds of strategies may work for them. And so the first part of the talk really, I guess, makes the point that making sense of data can be just too complex. Even if we have millions of users, even if we have billions of impressions, there are some key fundamental problems that cannot be inferred just from a lot of data. And so then the logical question then becomes, how do we then reason about these kinds of paradoxes, right? And the good news is that people across different sciences have spent a lot of time on this. Even before we had so much data, there were philosophers like Aristotle and Hume who were sort of thinking about what does it mean to cause something? Like, what is it that we want to know when we say we want to discover the cause or we want to know the scientific understanding for some effect? And this sort of applies in medicines. If you have a drug, you want to know how well this drug does. All you get to see is sick patients going to hospitals and getting drugs. In the social sciences, you want to know how well your economic policies are doing. Would making the exchange rate higher or lower make your economy better or not? Happy to do an experiment, but most likely people won't allow you to do it. And then similarly in genetics, you want to find what's the effect of genes on disease. So there are just lots of examples, not just in online systems, but almost every part of science, which thankfully has contributed to our understanding. So I won't go into the details. There are two very, very well-established frameworks. The first one is causal graphical models, which we were using, because we were sort of looking at each of these effects in terms of graphs. And there's also potential outcomes framework. So if you're interested, you can sort of go into the details of how it works. I'm going to give examples. So for us, it's not a philosophical question. We are very practical. This is a data engineers conference. So we just have a very practical causal meaning. We want to know if X causes Y whenever change in X causes necessarily a change in Y. And then all we want to estimate is the magnitude by which Y changes. So if X is your new algorithm, or X is your new UI, we just want to know how much does changing X cause a change in Y, which would not have happened if you hadn't changed X. Simple definition. And so what it will force us now to do is to think in terms of counterfactuals. And this, personally, I found the most important concept to think of these problems is whenever you make a decision or whenever you're thinking of improving something, just think of the question, what would have happened if you did not do that? Or what would have happened if you actually did that and maybe increase the intensity or decrease the intensity? And once we ask these what-if questions, it becomes much clearer about what exactly are we doing and also how much do we think practically it's going to have an effect. So what comes, I'll just try to explain the power of these methodologies using two separate examples. The first one would be, can you evaluate the impact, right? So you can think of two questions. So one is that you just want to know there's something in the world, like a recommendation system. You just want to know how much effect it's having, right? Because that'll help you decide how much resources to put in that. Then there are other things that you may want to do is that you may want to design a recommender system in a way that it takes causal inference principles into account, right? So the first part, I'm just going to say, if you already have an existing system, how to evaluate. And then we'll go to how do you then just design something from causal principles, because I think that's exactly what a lot of us should be doing. It just becomes very hard to do it. So why does it become so hard? I've already given some examples, but I think this picture, really this cartoon, gets to the heart of it. Here's the problem. We have an old algorithm, or we had an old policy, and it gives us some outcome, number of clicks. We then think, well, change the algorithm we change the algorithm, we get new recommendations, we get better clicks. But we didn't solve the problem, because our question wasn't to compare the new from the old above. Our question was really to compare if you had the new algorithm and in a counterfactual world where you did not have a new algorithm, what was the difference, right? So if this was Toys R Us, they had their clicks in November, and they had their new clicks in December. But really, I want to know what were their clicks in a different world, a different counterfactual world, where they cloned their customers and then showed them nothing in December. That's what I want to know. And you can clearly see it requires changing laws of physics to actually estimate these effects. So what people have done is, and I'm sure all of you are familiar with, are A/B tests, right? You say, I cannot clone users, but what we can do is randomly assign what people see to, in these different conditions. And the argument is that as long as your coin is random, if you show some users the new algorithm, if you show some users the old algorithm, on average, there's nothing different between random user 1 and random user 2, so it's all good. And this works brilliantly and across all different concepts, but the only problem is that experiments are hard to do. And sometimes they're just infeasible. So think of an experiment to determine if a subscriber on Amazon or Netflix actually shops more or watches more videos. The only way to do an experiment like this is to artificially make some people subscribers who are not, and artificially make some people who are subscribers non-subscribers, right? And you can imagine going to Amazon and asking them to do this with Amazon Prime and see their reaction, right? So then you need to have some other method of doing this. Another thing that comes up is that it may just be unethical, right? Suppose you're Amazon and you want to find out the subscription price for Amazon Prime. Should it be $99? Should it be $80? Should it be $50? Well, simple. You just do an experiment. That's what economists would tell you. But what you would not expect is that a lot of customers may lose faith in you, because just because of random chance, some had to pay much more for membership. Some had to pay much less for membership. And then it can also sort of just be inconvenient. If you're changing a UI element, it can just drive users away if it doesn't work, right? So then the natural question becomes, what can you do with just observational data? I showed some examples where you can just keep conditioning. So if you have very good idea of how your system was built, hopefully because you built it, then you can keep on conditioning on things that you think would matter, like activity level, time of day, so on. But it's sort of a rabbit hole. I mean, you can always approximate the truth. You'll never be able to get to the truth. The other approach, and this is sort of recent research work that's been developing, is that you can somehow find randomized experiments in the observational data. And so the basic approach is that we can't do experiments, but what we can do is find as if random events that happen in the data set that you're interested in. So here, for example, if you want to calculate the effect of a recommendation, what you can do is that you can exploit some naturally occurring variation, like imagine Jon Stewart suggesting a book on his show, right? What will that do is that it'll create this sort of an artificial shock to your book system or a book website, and then you can just see how much of that flows through the recommendation system to other books, right? So instead of doing an experiment where you sort of artificially put a lot of users in one condition where they had to see a book and see the effect on recommendations, you can use Jon Stewart, Oprah Winfrey, anyone who just creates these unnatural conditions in your data set, but then helps you to see the spillover effect on recommendations. And it turns out that these external shocks can be used to estimate the counterfactual, because it's pretty clear that if Jon Stewart had not sent a lot of people to this book page, it is very unlikely that they would have also clicked on to the recommended books without the recommendation system, right? Make sense? So if there was no recommendation, people would have only seen the first book. Because of recommendations, they saw other books, and so you can estimate the effect that way. And here's, again, the causal graphical model. You can actually prove it, but I'm just going to go as schematic. In general, visits to a book or an app are just confounded, because visits can cause recommendation clicks, but just demand in itself is correlated, right? Because that's exactly why you were recommending them in the first place. The visits could happen anyways, right? The nice thing is that when you have a certain shock, what happens is these visits become very high, right? So suppose this was your first product, app 1, that had a spike, a huge increase in traffic, and you can make a clear case that if demand for app 2 remains constant, then additional views to app 2 would not have happened without this recommendation system that was actually just showing people recommendations to click on, right? So just based on this very intuitive strategy, you can have a method that describes this effect. And this is just detail. You can actually just show that this effect would be equivalent to an effect of removing the recommendations from that page and comparing those two counterfactuals. But then the problem is, and I think as some of you might also think, is that this is a very odd approach. Like this, you're sort of taking these very, very odd things that happened in your data set and computing something on those small set of shocks, right? So in some sense, it may not be as satisfying. So what you can do is then you can try to increase the breadth of what you can do. But really, the upshot is that if it's possible, do randomization. But if it's not, then you can consider these creative methods of finding experiments in your data. And in fact, what I've been finding in my recent research, and I'll have some papers at the end, is that you can actually do this in a data mining way. You can sort of just use an algorithm to find these unnatural effects. But in some sense, it still is unsatisfying because now we know that this recommendation system may not be working as well, or maybe it's working great. But then what do we do with it? How do we come up with a new, better algorithm that should replace it, right? And here, I think there's been a lot of work which shows that what you should really do is just think of systems as continuous experiments. And what this means is that, let me take an example of gambling. If you've gone to these casinos, what you would find are these sort of slots in the casinos. And you just pick one slot. At random, you get some reward, right? Now, assuming you were an algorithm, right, what you might think of it is that whenever I pick one slot, which is I show one recommendation, I get some reward. It's a click or it's not a click, right? So what you can just do is, over a period of time, you can just randomly select different of these arms and figure out which arm works the best, right? So this sort of requires a change in the way we think about algorithms, because what it's saying is that there's no one good algorithm. And maybe it's not worthwhile to find one good algorithm. What we should really be doing is that we have a list of items to recommend. What we're going to do is we're going to just randomly recommend maybe each of these items in turn, and then find which ones people like and which kinds of people like which items. And as we learn that, we're going to keep showing more and more of that strategy and less of the other strategies that we tried out. And it sort of keeps playing on. So the most simplest algorithm that you could implement with such kind of an approach would be Bandits. And what this does is, the old algorithm was showing you some recommendations. It says, I don't trust this algorithm. I would not even trust a new algorithm that comes in its place. So here's what I do. I would show whatever I think is the best algorithm right now to most of the users. And then I'm going to show whatever is a random algorithm, completely arbitrary, to the rest of the users, right? And the idea is that by showing the right algorithm to most people, you're exploiting, right? And this is the world we are always in. We are always exploiting. We predict well, and we show people always that. But then we also have this exploration here, which is saying that that algorithm is great, but I'm just going to test new strategies, random strategies, on other people. And you can, again, theoretically show that if you always do this, you can sort of have a feedback loop where this strategy informs your current best algorithm. And it sort of keeps on improving every day, every second. And a simplest algorithm for this would be something like this. With low probability, you show a completely random item to a user. This is where you're learning. And with high probability, you show the current best output from the algorithm. And then essentially, if you want to think of it, in some sense, your system is learning as it's proceeding. So instead of having a train test, it's sort of learning with, as it gets new items, it tests it on its users, and then feedbacks in to the actual algorithm. And this is also practical. Just like the last one was used successfully on Amazon's recommendation, this is being used on MSN. So for example, here this is Yahoo homepage, and there's a paper that shows how this can work for showing different news articles as recommendations. And finally, I just want to close with a very, very strong warning. In the last 2 parts of the talk, I presented 2 methods that work well. And so you might get the impression that if you're using those methods, you'll be doing mostly correct in terms of causal inference. But I would be a little skeptic for this graph. And I think that if one thing that you want to take from this talk, I would prefer that you just take this graph in your heads. And this graph is very compelling because it shows that computer science doctorates awarded in the US and the number of revenue generated by arcades is almost perfectly correlated. And you might just say, oh, that's not right. That doesn't make sense. But we know this because we have some sense of what's going on here. We know that, well, we hope that computer science PhD students are not motivated by arcades. But this could be any time series, right? This could be any 2 variables in your data set. And if you're not careful, and if you don't have an intuition on what's going on, you'll be in trouble trying to interpret these things and also predicting based on these things. And so really, always be skeptical of causal claims from observational data, actually from any data. And then another thing which is quite true is that more data may not necessarily improve your causal effects. It might just make you more sure of wrong results. And that's it. Thank you.
We have time for 1 or 2 questions. If anyone has them, I can bring the mic over to you.
Yep.
I just wondering, you mentioned low activity and high activity. How did you define?
Can you speak a little louder?
You mentioned a high activity and a low activity. How did you define the low and high?
I see. So the question was, in the example for recommendations, we divided people into higher activity and lower activity. That was just based on what the people in the product team were using already. So it was essentially, if I remember correctly, 10% of the users were higher activity users, and then everything else was lower activity. But I think the larger point is that those specifics do not matter that much, because you can also imagine another study where you do 20%, where you do 30%, right? I think a key insight for us was that it changes and flips based on what you select. But you can use any cutoff.
How long should you run the multi-arm bandit you called it explore exploit? How long should you explore for and then exploit, like with that, so you avoid some kind of stigmergy or something like that?
So I think the question was, in multi-armed bandits approach, how long should you keep being on exploring exploit? I think that really depends on how important you think is getting the right answer. But maybe another approach is to think of a case where these distributions are keeping on changing over time, right? So maybe the right answer is to just say that I'm going to run this always, and the only thing I'm going to change based on my confidence is the percentage of time I'm exploring and the percentage of time I'm exploiting. But I think it sort of requires a key philosophical shift almost in the way we think about algorithms. Because first, it needs some humility to know that you don't have the best algorithm. And second, it's this sort of weird scenario where every day is an experiment going on, and it's sort of a self-learning system. But I think it's really important because in some cases, it might be not that interesting. For example, if you're trying to predict someone's credit history, it's not changing day after day. But think of if you're trying to predict cases like what people like in music, right? Or what people are trying to do with news. These things change very quickly. So what's interesting today may not be interesting tomorrow. So it doesn't make any sense to say that the prediction algorithm was working yesterday would also sort of keep working as people's preferences change. So maybe the answer is to sort of always do explore exploit.